So last time we talked about the concept of antiderivative, basically going back from a derivative to the original function. We saw that we had to put in a plus a constant every single time we took a derivative. For instance, if we're looking for a function whose derivative is 2x, it could be x squared, but it actually could be x squared plus any number. Right now I want to talk about some rules for taking derivatives. Last time we just took our experience taking derivatives, and I want to now come up with some rules for taking antiderivatives. So let's start off with just a few. The antiderivative of any constant is just, now let me call the constant a, is just ax plus a constant. Because if I take the derivative of ax, I just get a. So if I take the derivative of 5x, I just get 5. And if I take the derivative of a constant, I get 0. So the antiderivative of any constant is just of a number times, the antiderivative of any constant is just that constant times x plus another constant. Let's talk about what's called the antiderivative power rule. So the antiderivative power rule, the antiderivative of x to the n is 1 over n plus 1 x to the n plus 1 plus a constant. And you can see that this only makes sense, especially this part right here, if n is not negative 1. If n is negative 1, then I end up with 1 over negative 1 plus 1, that's 0. So I can't use this on x to the minus 1, which is 1 over x. This cannot be used on 1 over x, which is x to the minus 1. But it can be used on any other power. For example, the antiderivative of x to the 1, according to this is x to the 1, x to the 1 is just x, is 1 over 1 plus 1, x to the 1 plus 1 plus a constant. In other words, you probably wouldn't even write this. You'd probably write 1 over 2, 1 over 1 plus 1 is 2, x to the 2 plus a constant, which agrees with the solution to when we did this problem the last time. Let's just do one more using the antiderivative power rule. Let's take the antiderivative of x to the 10th. We'll do a couple more actually. Here n is equal to 10. Take a moment and finish that problem. You can always pause the video when you want to do a problem. This is going to be 1 over 10 plus 1 x to the 10 plus 1 plus a constant. Let's do yet another one. How about the square root of x? Before we try to take the antiderivative, let's rewrite the square root of x as a power. That's x to the 1/2. I haven't done any calculus yet. That's why this symbol, which is called an integral sign, is still there. That's why the dx is still there. All we did was we changed root x to x to the 1/2. That's just algebra. Now let's go ahead and use the antiderivative power rule. So we're going to have 1 over 1/2 plus 1 x to the 1/2 plus 1 plus a constant. Let's simplify that a little bit. 1 over 1/2 plus 1, that's 1 over 1/2 plus 2/2, 1 over 3/2. 1/2 plus 2/2 is 3/2. X to the 1/2 plus 2/2 is 3/2 plus a constant, and we can simplify that even a little bit more. 1 over 3/2 is just, we just flip the bottom. This is just 2/3 x to the 3/2 plus a constant. So this is a very powerful rule. Let's use it again. Let's take the antiderivative of x to the minus 2. Remember, the only power you can't use it with is x to the minus 1, but we can use x, we can do it with x to the minus 2. I could have just as easily written this problem as 1 over x squared. 1 over x squared is the same as x to the minus 2. So two ways of writing exactly the same problem. According to the antiderivative power rule, this is going to be 1 over negative 2 plus 1, x to the negative 2 plus 1 plus a constant. And if we simplify that a little bit, we end up with 1 over negative 1, x to the negative 1 plus a constant. In other words, negative 1 x to the minus 1 plus a constant. In other words, minus x to the minus 1 plus a constant. I suppose that's just about as simple as it gets. You could possibly write this as minus 1 over x plus a constant if you like. I don't know if you like the looks of that better. So the antiderivative power rule, a very, no pun intended, but powerful rule. We said that the only power you can't use that with is negative 1. So let's see what the antiderivative of x to the minus 1 is. Since we can't use the antiderivative power rule on it because we end up with division by 0 right there. So the antiderivative of x to the minus 1, which is the same as the antiderivative of 1 over x, antiderivative of x to the minus 1, antiderivative of 1 over x. This is just the natural log of x plus a constant, which you knew it was because you know that the derivative of the natural log of x is 1 over x. So you knew that that would be the antiderivative. Now in calculus 2, you might write that even a little bit more comprehensively, and we'll explain why in calculus 2 for those of you moving on. You can actually write that this is equal to the natural log of the absolute value of x. I'm not saying that that and that are the same because they're not, but this is actually in some sense a better antiderivative of that than this is for reasons which we can talk about next semester if you happen to be in calculus 2. So we have the antiderivative of a constant, the antiderivative power rule, and the one power that you can't use the antiderivative power rule on, 1 over x, in other words, x to the minus 1, we can work out the antiderivatives of each of those. Let's now talk about two rules that you've seen over and over again. The antiderivative of f of x plus g of x dx is equal to the antiderivative of f of x plus the antiderivative of g of x. And this breaks up, so we're saying antiderivative breaks up over plus, and also breaks up over minus. Just like derivative did, just like limits did, just like limits at infinity did. We've seen a lot of things this semester which are broken up over plus and minus, and we have a rule that always follows that one, or goes in front of it, depending on what order we rewrite it in. The antiderivative of a times f of x. If you have a constant times a function, you can pull the constant right through the antiderivative symbol. These two always go together, and together they're known as linearity. And as I've said many times, some of you are going to find yourself in a course called linear algebra, which is all about this property, these two things put together. So with these, and with the antiderivative power rule, now we're in a position to be able to take the antiderivative of any polynomial. So let's take a look at a few examples. How about the antiderivative of x squared plus 3x plus 5. I'm going to do this slowly right now, using all the rules individually, but at some point you're just going to get to the point where you can pretty much write that down as quickly as you write down the derivative of that. So according to this rule, breaking up, let me change this plus to a minus. Now we have 1 plus and 1 minus. This is going to be the antiderivative of x squared plus the antiderivative of 3x minus the antiderivative of 5. And in this next line, I'm just going to go ahead and pull the 3 through the integration symbol. Antiderivative of x squared, so I'm not changing anything there. 3 times the antiderivative of x minus the antiderivative of 5. And we have rules for each of these. I can use the antiderivative power rule on that. Here we have a 2, so it's going to be 1 over 2 plus 1, 1 over 3 x cubed. That's a 3 in case it's not showing up well. Plus 3 times, here we have an x to the 1. 1 over 1 plus 1 is 1 over 2. So 3 times 1/2 times x to the 1 plus 1, that's 2. And we said that the antiderivative of a constant was just the constant times x. And finally, we'll put in our plus c. You don't have to put in the plus c 3 times. You don't have to add a constant 3 times. You might as well just add it once. And let me just go ahead and simplify that slightly. That's going to be 1/3 x cubed plus 3/2 x squared minus 5x plus a constant. So that's 5 rules altogether so far. Let's keep adding rules. Rule number 6, the antiderivative of sine x is negative cos x. The antiderivative of cos x is positive sine x. Oh, forgot my plus c. So the antiderivative of sine x is negative cos x. The antiderivative of cos x is positive sine x. Notice that the signs are opposite to what they are when you're taking derivative. When you take the derivative of sine x is plus cos x, and the derivative of cos x is minus sine x. Here it's reversed, and based on past experience, this may mess you up for just a little while. Try to get it straight in your head that when you're taking the derivative of sine is positive cos, but when you're taking the antiderivative of sine is negative cos. Just try to get that all straight in your head. The antiderivative of secant squared of x, we did this one last time as a problem. Now I'm going to ask you to memorize it as a rule, is tan x plus a constant. Because you know the derivative of tan is secant squared. And a few more involving exponentials. The antiderivative of e to the x. I bet you don't have to work too hard to guess what the antiderivative of e to the x is. What do you take the derivative of e to the x? What do you take the derivative of to get e to the x? Well, e to the x, of course, plus a constant. The antiderivative of a to the x is 1 over the natural log of a times a to the x. So when you take the derivative, you multiply the original function by the natural log of a. Here we multiply by 1 over the natural log of a. In other words, divide by the natural log of a. And one more. The antiderivative of ln of x is x ln x minus x. You can check that one out for yourself. If you take the derivative, let's just take the derivative of x ln of x minus x. Well, the derivative of this first part we take by the product rule. First times the derivative of ln of x, which is 1 over x, plus the derivative of the first, which is 1, times the second, which is ln of x, minus the derivative of x, so minus 1. X times 1 over x is 1 plus ln of x minus 1. Oh, forgot my plus constant here. And this equals ln of x. So the derivative of this really is that. So this really is an antiderivative rule.